Hello everyone, welcome to the lecture 8 in the course Diffusion in Solids. So last class we started looking at some of the problems related to the diffusion equations. We saw how to solve the thin film sandwich geometry and instantaneous source and so on. So today, continuing that, we will take a couple of more scenarios. One is known as the constant source problem, another is the diffusion couple analysis. So here are some of the keywords. So the constant source problem, one direct application is actually when it comes to the carburization process. Some of you who know a little bit about the physical metallurgy of steels, you know that the steel which is an alloy of iron and carbon. So quite often we need to strengthen only the surface. So that is done by increasing the carbon content only at the surface. The hardening of the surface makes it more resistant to wear and so on. So this carburization involves allowing the carbon to diffuse into your steel sample and depending on how much depth you want to achieve with an extra carbon, decides how much temperature and time you want to do it. So the problem can be stated like this. A steel piece is being carburized by maintaining constant gas flow at the surface at a temperature T for a duration small t. The surface concentration of carbon is maintained at Cs and the carbon content of steel is C0. So now what we have to estimate is the concentration profile of carbon as a function of diffusion depth x and time t. So we can draw the picture is like this. So here you have a Cs and this is the carbon content in the steel which is C0. Now the geometry as you might already notice in this case, because we are maintaining a surface concentration constant and that is done by either flowing gas or by putting this piece in a solid pack carburizing like people do in the carbonaceous atmosphere. So that here always at the surface you have a constant concentration. This is why it is referred to as constant source. And our assumption that we make earlier that the diffusion depth is much smaller than the overall dimension of the sample still holds true, and that's why it can be considered in the semi-infinite domain. So the initial condition, that means at time t equal to 0. So at c x comma 0 is Cs when x is equal to 0, whereas C of x comma 0 is C0 when x is greater than 0. Remember, C0 is the carbon content in the steel. Now let us write the boundary conditions. So the boundary conditions state that at 0, see x equal to 0, anytime t the concentration will be Cs. That's what we mean by the constant source. So always at the surface the concentration is Cs. And at the infinity, that means towards the end of the sample, always at any given time the concentration will be C0. So now since it's a non-steady state condition, we have to use the Fick's second law and we assume a one-dimensional diffusion. So like we did in the last lecture, let us use the Laplace transform of the Fick's second law. Remember that we use Laplace transform because now with Laplace transform we have converted a partial differential equation which was Fick's second law to an ordinary differential equation which has only one variable x. So now this equation dou square c bar by dou x square minus p c bar by d plus c of x comma 0 by d equal to 0. Now as per the boundary conditions we have that c of x comma 0 is C0. Now we substitute this and then what we get is d square c bar by dou x square minus p c bar by d plus C0 by d equal to 0. So if I take p by d common here, I can write it like this: dou square c bar by dou x square minus p by d multiplied by c bar minus C0 by p equal to 0. Which implies that dou square c bar by dou x square is equal to p by d times c bar minus C0 by p. So as we also saw this kind of differential equation in the previous class, we can write now that c bar minus C0 by b must be equal to k into e power minus root p by dx. Okay. So, now our job is to evaluate what is k. Now, how do you evaluate what is k? So, for that what we need to do is basically, let us go to the definition of the Laplace transform itself, which is c bar is nothing but it is 0 to infinity c of x comma t e power minus pt dt. Now, for x equal to 0, the c bar of 0 let us calculate. So, c bar of 0 is equal to 0 to infinity c of 0 comma t e power minus pt dt. And from the boundary conditions we know that c of 0 comma t is nothing but Cs. So, taking it further, I can write c bar of 0 is equal to Cs, Cs can be taken outside, 0 to infinity e power minus pt dt. Now, you may remember this simple integral from even our lecture 4. So, this is nothing but 1 by p. So, therefore, c bar naught is equal to Cs by p. So, this is our equation number 2. Now, if you combine equation 1 and equation 2, this is equation 1. So, here if I put x equal to 0, here I get c bar minus c naught by p is equal to k. Okay, and c bar 0 value is Cs by p. So, therefore, combining these two, I will get k is equal to Cs minus c naught by p. And therefore, what I can write is c bar minus c naught by p is equal to Cs minus c naught by p into e power plus minus root p by d times x. Now, till now we have only evaluated k. We still have to find out the inverse of this c bar. So, since we know that the domain of the problem we have only x greater than or equal to 0. So, therefore, we only need to take one of the signs, which is the minus sign, and you can check that only in the minus sign you will satisfy the boundary condition that at x equal to infinity the this becomes 0. So, now we can write c bar minus c naught by p is equal to Cs minus c naught by p multiplied by e power minus root p by d times x. So, that means that c bar becomes Cs minus c naught multiplied by e power minus x by root d into root p by p plus c naught by p. Not much I have done, I just rearranged a little bit. So, what it helps me is this we call as equation number 3. Now, if you refer back to your Laplace transform table which was given in lecture 4, you will see that if f of t is equal to 1 minus error function of a by 2 root t, then Laplace transform of f of t is equal to e power minus a root p by p. So, this is equation number 4. So, now if you compare the RHS of this equation e power minus a root p by p to the RHS of the equation here, this term Cs minus c naught e power minus x by root d root p by p, you will see that we can write a is equal to x by root d, and therefore, the Laplace inverse of this term is nothing but Cs minus c naught into 1 minus error function x by 2 root dt. Now, we have another term which is the c naught by p. So, inverse of c naught by p is equal to c naught. So, this we have already seen before. You can check once again why it should be c naught. So, therefore, now we can write that c of x comma t is equal to Cs minus c naught 1 minus error function x by 2 root dt plus c naught. It can be written, it is usually written in this form, c of x comma t minus c naught by Cs minus c naught is equal to 1 minus error function x by 2 root dt. And if you plot, this is how this profile will look like. You have T1, T2 and T3. T1 is less than T2 is less than T3. And you may notice that if we do for the same steel at the same temperature in the same carburizing atmosphere, then you will have the relation x1 square by T1 is equal to x2 square by T2. Okay, and similarly it can be x3 square by T3. So now if we move to another problem, which is called as a diffusion couple problem. Now in this case, the problem is something like this. Two blocks of alloy AB and pure metal A. That means you have one block of alloy AB, one block of pure metal A are joined together. The assembly is heated isothermally at a temperature T for a time small t. Now what we have to determine is the composition profile of B, assuming that diffusivity of B is much greater than diffusivity of A at the given temperature. This is important assumption, otherwise this mathematical framework of problem changes, and it cannot be actually solved very simply. So this assumption is important, and we will see what happens when this assumption is not valid. This is another process we will take up in the coming weeks. So this I have represent pictorially here, and here you can see the initially it was AB here with some concentration of B as Cb naught. Then after that you anneal at temperature T for a duration small t, then the composition of B develops like this. So you will see that here in this region it starts reducing, here in the block A it starts increasing. So this is because of the diffusional process. So again geometry is a semi-infinite diffusion couple, because you assume that some part of A is not affected, the B does not reach there, which means that the diffusion depth is much smaller than the dimensions of the sample A. What are the initial conditions? So initial conditions are like Cb of x comma 0 is 0 when x is greater than 0. That means if I have my origin is here, so at x equal to at x greater than 0, initially I had 0 content of B because this was pure A, and at x less than or equal to 0, I had Cb content equal to Cb naught, which is basically the alloy composition. The boundary condition is at x equal to infinity, Cb infinity comma t is 0. Now it is a non-steady state, Fick's second law can be used. So assumptions is as I said, dB must be much greater than dA, and also that the concentration of B is not very large. So these two factors can actually influence the mathematical analysis, which we will see later also in the lectures. So for now, how do we go about it? So this is a slightly different approach to solve the problem. When I say slightly different, it means different than what we have done till now. That what we do here is, so let us take one slice of from this region here, which is at a distance x bar from the origin. So I take a slice here, and this slice is of thickness dx bar, and this is located at a distance x bar from here. And this is actually situated at a distance x. So now at a distance x from the origin, the concentration is Cb x comma t. So therefore, this is what I already explained to you. So the concentration developed due to this thin element here at a distance x from origin is dCb x comma t. Okay, remember why I am writing it dCb is because I am assuming that this concentration is developed to this due to this thin source, which is of thickness dx bar. And remember that x bar is on the negative side. So now if you recollect that due to the thin film source, what is the basically the concentration developed, assuming a unit cross section, you can write dCb x comma t is equal to dmb by 2 root pi dt exponential x minus x bar whole square by 4 dB t. So this is exponential minus x minus x bar whole square by 4 dB t, and we know that dmb is equal to Cb naught into dx bar, assuming a unit cross sectional area. See, mb is the amount and Cb is concentration or amount per unit volume. So when we multiply Cb naught by volume, which is dx bar, which is the thickness, into a unit cross sectional area, we get the amount. So this dmb can be written as Cb naught into dx bar. So dmb is nothing but the amount of B contained in thin slice of thickness dx bar. So now moving ahead, the total concentration. So see, what we are doing is the total concentration Cb is then the sum of concentrations developed due to all such thin film sources which are extending from minus infinity to 0. I will just for your ease of understanding. So what we have here, that at this point, due to this thin slice dx, the concentration that is developed is dCb x comma t. Now at this point, concentration developed due to several such thin sources, because there will be several such layers. So due to all these layers, the concentration developed here is given by when we integrate this whole term from minus infinity to 0. Why minus infinity to 0? Is because we are integrating over, or we are considering accounting for all the thin film sources which lie from here to here. Okay. So that's why minus infinity to 0. Now, how do we solve minus infinity to 0 and this integral? So again, I'll just write the minus sign here so that there is no confusion. So this is exponential minus x bar x minus x bar whole square by 4 dB t dx bar. Now let us substitute x minus x bar by 2 root dt as u. To solve this integral, we make use of the substitution method. Some of these concepts I showed you already in the mathematical concepts lecture. So therefore, if I differentiate minus dx bar is equal to du into 2 root dbt. Remember again here, the variable, the integral variable is x bar, not x. Okay, because we are integrating for all such slices which have this thickness x bar, dx bar, and they are located at a distance of x bar. So the variable is x bar here. So minus dx bar is equal to du into 2 root dbt. Now when x bar is minus infinity, the u will be equal to infinity, because here you see the way it is defined. When x bar I put minus infinity, u will be infinity. When x bar is 0, u will be equal to x by 2 root dbt. Now Cb of x comma t is equal to Cb naught by 2 root pi dbt. So this is the function here, and now the limit I change from infinity to x by 2 root dt exponential minus u square du into minus 2 root dbt. Now further moving ahead, I can just simply write, you see that 2 root dt and 2 root dt gets cancelled, and because there is a minus here, I can change the I can remove the minus if I change the limit of the integral. So I put it x by 2 root dt into infinity. Now how do we still solve this integral? So to do that, what we actually do is we split this integral into two parts. So Cb of x comma t can be written as Cb naught by root pi x by 2 root dt to 0 exponential minus u square du plus 0 to infinity exponential minus u square du. Further, I can slightly change the limit of this integral, and I can write Cb x comma t Cb naught by root pi 0 to x by 2 root dt. I just reverse the limit, and therefore I put minus here exponential minus u square du plus 0 to infinity exponential minus u square du. Now you may be wondering why I am doing this. So the reason for doing this is because there is a function which already we saw in the constant source problem, but we did not discuss elaborately what this error function means. So this error function actually is a function which is defined for a, let's say, for a z. So it is defined as error function of z is equal to 2 by root pi 0 to z exponential minus u square du. So it basically defines the integral, if you think of integral of the Gaussian function. Okay, so error function of z is equal to 2 by root pi 0 to z exponential minus u square du. If you use this now here, you will see here that 0 to z for this integral, it is 0 to x by 2 root dt. So, this becomes error function of x by 2 root dt. Here it is 0 to infinity, it becomes error function of infinity. Just to tell you, error function of 0 is 0, error function of plus minus infinity is plus minus 1, and error function of minus z is equal to minus error function of z. So, therefore, I can write, and remember that in the error function definition there is a 2 by root pi here. So, when I replace this by error function here, I have to also multiply by root pi by 2. That is why this root pi gets cancelled and I get CB naught by 2 minus of error function x by 2 root dt plus error function of infinity. Now, since error function of infinity is 1, I can write it as CB of x comma t is equal to CB naught by 2 1 minus error function x by 2 root dB t. So, here this is what the final solution looks like. One activity question for you is that can you try and plot the graph for error function of z versus z, how the plots look like. Okay. So, this you can maybe just try. So, this is what we have taken up as two problems for this lecture, and in the next video we will take a couple of more examples which correspond to the finite domain. So far we have talked about the infinite, semi-infinite domain. Next week we will talk about two more problems. So, thank you.